Did it work?
Yes.
Okay, hello everyone. Today I'm going to talk about when is it possible to graduate? Well, as you'll see, this is really a topic about what's called a super task. You'll see soon enough. So as um, our host explained in the introduction, I got my bachelor's degree from UCLA. I'd like to start by telling you a little bit about the curriculum at UCLA. So it's a rather peculiar system. They start with a course called Math Zero. After completing Math Zero, there's a course called Math One. After Math One, there's a course called Math Two. After completing Math Two, there's a course called Math Three, and so on and so on and so on. There's one math course, indeed, for every natural number. And in order to graduate from UCLA, you have to finish all of the math courses. Seems extremely ambitious. How can you complete infinitely many math courses in only 4 years? Well, let me show you. Like any good student, the key to success is procrastination. That means that when you're confronted with an extremely difficult task, you're lazy at the beginning, and then as the deadline gets closer and closer and closer, you get increasingly desperate, and then you have to work harder and harder and harder. So the very first course, Math Zero, you think, oh, okay, there's plenty of time, there's 4 years. Let me take it really easy, you know, sleep in a lot. And so I took 2 years to complete Math Zero. Then, well, okay, so there's only 2 years left, so I better work a bit harder. Math One, I take 1 year. Math Two, I have to work even harder, so I take half a year. Math Three, I take a quarter of a year. So the pattern is that each course, I have to work twice as hard so I can finish in half the time as the previous course. And if I follow that plan, then the total time to complete all the courses is 2 plus 1 plus a half plus a quarter, and then plus an eighth plus a 16th, and so on. This is a geometric series, and as you may remember from high school, the geometric series formula, the sum of all these times is in fact 4. So that is how you complete infinitely many courses in only 4 years. So then other schools have different sort of curriculum. For example, Caltech, they have one math course for every real number. So there's not only a Math Zero and a Math One and a Math Two and so on. There's also a Math Pi and a Math E and a Math Squared of 2. Every real number, there's a math course to complete. At U Chicago, they also have a similar set of math courses. There's also Math Zero, Math One, Math Two, and Math Three. But this time, the ordering of the courses is different. So instead of completing Math Zero before Math One, you have to complete Math One before Math Zero. But before you can do Math One, you have to take Math Two first. Oh, and before you can start Math Two, you have to complete Math Three, so on. At UIUC, which is the sister school to UIC, the one where I got my PhD, there's actually only two math courses, Math 0 and Math 1. But there's a rather strange structure here. You see, Math 0 is taught by a very distinguished professor who insisted that his course was more advanced, and therefore the other course, Math 1, should be taken before Math 0. Math 1 is also taught by another very distinguished professor, but he strongly disagreed with the assessment, and he said that his course is more advanced, and so Math 0 should come before Math 1. So they argued and argued, and at the end, the compromise they came up with was that Math 0 should be taken before Math 1, and Math 1 should be taken before Math 0. It's a rather strange situation. So all these examples inspired me to formulate the following problem, which I call the graduation planning problem. So suppose we're given a curriculum, C, which is just a set of courses, and also suppose we're given a prerequisite relation. So when I write X, right arrow Y, that means that course X must be taken before course Y. And the goal is to devise a graduation plan. So that is a sequence of time intervals, T0 start, T0 end, T1 start, T1 end, T2 start, T2 end, and so on, such that, so you always have to start, no earlier than time 0, and you always have to finish no later than time 4, and every course has to be completed somewhere in one of these intervals. Now, there are some rules to follow. First of all, you have to follow the prerequisite relations, which means that if X is a prerequisite for Y, then X has to be completed before Y. 2, each time interval has to have positive duration, so you cannot complete a course in 0 time. You always have to allow some positive time. And 3, you can only take finitely many courses per interval. Now, I should say that if you can complete finitely many courses in an interval, then you can reduce to the case of completing only one course in an interval, right? So if you take n courses in an interval, you might as well split the interval into n equal pieces and complete each course in one of those little pieces. So for the rest of the talk, I'll assume that you're only completing one course per interval. And the main question is this: for which curricula does a graduation plan exist that obeys these rules? And here's the main theorem, which is the answer to that question. A graduation plan exists if and only if the curriculum is countable and well-founded. So I'm going to explain what both of these terms mean. A curriculum is countable if there is a list X0, X1, X2, and so on, such that any course occurs at some finite position in the list. So the list itself might be infinite, but if you're just looking for a specific course, you only have to search through finitely many before you find it. And the curriculum is well-founded if it contains no infinite descending chains. So let me go back a few slides to show what I mean by that. So the UChicago example, where you have the arrows pointing to the left, that is an example of an infinite descending chain, right? And the UIUC example, that's actually also an example of an infinite descending chain. So that's a loop. And if you have a loop, then you can always descend through the loop forever, right? And that'll give you an infinite descending chain. So the second and third examples here are contain infinite descending chains. Therefore, they're not well-founded, and therefore, it's impossible to graduate. Okay. Note that well-foundedness is equivalent to the following. If A is a non-empty set of courses, then there is some course X in A that has no prerequisites. So you should think to yourself for a moment why this is equivalent to there being no infinite descending chains. Right? If there is an infinite descending chain, then you could just take A to be the set of all the courses in that chain, right? And then there will be no course in there that lacks prerequisites, because by definition, you just follow the chain and you get a prerequisite for any course. And conversely, if you have an A that violates this condition, then you can just pick any course in there, choose a prerequisite to that course, and then choose a prerequisite to the prerequisite, and then choose a prerequisite to the prerequisite to the prerequisite, and so on, and you get an infinite descending chain. So that's why this condition is equivalent, well-foundedness. Okay, so I'm going to prove the theorem. So first I'm going to prove necessity, and then later I'm going to prove sufficiency. So why is it necessary for a curriculum to be countable and well-founded? Okay, let's consider well-foundedness first. So in the slide I said it's obvious, but think about this. So if there is an infinite descending chain, that means that we're in a situation like the U Chicago here. So that means that the curriculum contains a chain that looks like the second example here. Now, the problem here is that you can't start anywhere, right? So the moment you try to start any course here, you can't do it because you have not, because it always has a prerequisite, and you will not have done the prerequisite. So, and if you can't start the chain, you certainly can't finish it. So that's why well-foundedness is necessary. Why is countable necessary? Okay, so here's what I'm going to argue. If C is an uncountable set, and so C is an uncountable set of courses, for instance, and for each course, X, let's say that Tx is the time you need to complete the course. Then what I'm saying is that when you sum all the times, you get infinity. So why is that? Well, let me first establish the following fact. So if Cn is a countable set for every natural number n, and C is the union of these Cn's, then C is countable. And why is that? Well, it's proof by diagram. So, so suppose C is a union of these Cn's, right? So suppose that each row represents one of these Cn's. Since Cn is countable, you can write it as a list. So each row we can think of as listing the elements of Cn. And then how do we form a list of the entire C? Well, just follow this zigzag pattern. So start at the top left and then just follow the snake. And you can think to yourself that any position on this grid, right, will be reached at some finite after some finite number of steps. Therefore, the entire grid is countable. And since C represents the grid, C is countable. Okay. Now, to prove the fact, we're going to divide up the courses this way. We're going to let C0 represent all the courses that take at least 1 year. C1 will represent all the courses that take between half year and 1 year. C2 will represent all the courses that take between a third of a year and half a year. C3 will represent all the courses that take between a quarter of a year and a third of a year, etc. Then C is the union of all the CNs. Why? Well, every course has to take some positive amount of time. So that means every course has to take more than 1 over n plus 1 time for some n. So therefore it has to belong to one of these C's. Okay, so C is the union of the CNs. So if we apply the fact, it cannot be the case that every CN is countable. Because if all of the CNs were countable, then C would have been countable. But we assume that C is uncountable. So therefore, there's some n such that Cn is uncountable. Now, in particular, that means that Cn is infinite. So if there are infinitely many courses that take more than 1 over n plus 1 years each, then you get 1 over n plus 1 times infinity, and that's just infinity. So, yeah. That's why this fact is true. Therefore, uncountably many courses cannot be completed in a finite time. By the way, it's a well-known fact that the real numbers the set of real numbers is uncountable. Therefore, the first example here, the Caltech example, it's not possible to graduate because the set is uncountable. The curriculum is uncountable. All right, now comes the hard part, proving sufficiency. In other words, we have to show that every curriculum that is countable and well-founded has a graduation plan. So here's a first attempt at a proof. We're going to define something called a rank. So the rank of a course X is going to be defined as follows. If X has no prerequisites, we're going to say that the rank of X is 0. If X has only prerequisites of rank 0, then we're going to say that the rank of X is 1. If X has only prerequisites of rank 0 or 1, we're going to say that the rank of X is 2. If X has only prerequisites of rank 0 or 1 or 2, we're going to say that the rank of X is 3, and etc. These lines are in order of priority. So in order to find rank X, we should take the first bullet that applies. So if X has only prerequisites of rank 0, and it does have some prerequisites of rank 0, then, of course, the second bullet will be true, but the third bullet will technically also be true. But since we're prioritizing, the higher up the list, then we should take the second bullet, and we should say the rank is 1. Okay. Notice that if x is a prerequisite for y, then the rank of x should be less than the rank of y, right? The way we define rank is that all the prerequisites have lower rank. So here's the basic idea. We're going to partition the curriculum by rank. We'll devise a plan where we first complete all the rank 0 courses, and then we complete all the rank 1 courses, and then we complete all the rank 2 courses, and etc. So borrowing from my experience at UCLA, we're going to say that we're going to finish all the rank 0 courses in the first 2 years. Then we're going to finish all the rank 1 courses in half the time of that. And then we're going to finish all the rank 2 courses in half the time of that. And then we're going to finish all the rank 3 courses in half the time of that, and so on. All right. Fix any given rank n. No rank n course is a prerequisite for any other rank n course, right? Because if it were a prerequisite, it would have to have lower rank. So that means we can do the rank n courses in any order we like. Now, since there are only countably many courses in the curriculum, there are certainly only countably many courses of rank n. So we can choose a listing of the courses of rank n, and then using the cramming idea that we saw at UCLA, we can shift and scale the plan to fit inside the time interval that we decided in the previous paragraph. And therefore, we'll complete all the courses of rank n in that. And we do this for every n. Success? What do you think? No, I'm afraid not. So what's the flaw here? Well, the flaw is that rank n courses for all finite n might not exhaust all the courses in the curriculum. Here's an example. Suppose that our curriculum's like this. So there's a math n for every natural number n, just like at UCLA, but there's one more course. Let's call it physics 0. And physics 0 is above all of the math courses. In other words, in order to start physics 0, you have to complete all the math courses first. It's easy to show that in this curriculum, the rank of math n is just n. But what is the rank of physics 0? Well, it should be larger than the ranks of all of its prerequisites. That is, it should be larger than n for every natural number n. So it should be larger than all of the counting numbers. Well, obviously, there's no such natural number, right? So that means that if we were to follow the plan in the previous slide, we would never actually reach physics 0, and therefore we wouldn't graduate. So how do we fix this? Well, the solution is we need to extend the counting system to allow numbers larger than any finite number. Set theory supplies such a system. Ordinal numbers. They are typically denoted with the first few lowercase Greek letters, alpha, beta, gamma, etc. Basic properties of ordinals. Well, first of all, ordinals are inexhaustible. If A is any set of ordinals, then there's some ordinal larger than any ordinal in that set. This is a much stronger form of infinity than the natural numbers. So the natural numbers are infinite, right? There are infinitely many natural numbers, but they're not inexhaustible because you can form the set of all natural numbers, and then there's no natural number that's bigger than all. But ordinals have this property. Secondly, ordinals are well-founded. Specifically, what that means is that if phi is any statement and alpha is the set of all ordinals such that phi is true of alpha, and this set is non-empty, so there's at least one alpha that makes phi true, then there's a smallest ordinal for which phi is true. Okay. So the consequences are, first of all, there is a smallest ordinal, and that's denoted by 0. For any ordinal, we can take just the set containing that ordinal, and by the inexhaustibility property, there are ordinals bigger than that. So for any ordinal alpha, there are ordinals bigger than alpha, and we can take the smallest one that's bigger than alpha. And that's denoted by alpha plus 1. In particular, 1, 2, 3, 4, 5, 6, and so on are all ordinals. If A is any set of ordinals, then there is a smallest ordinal that's bigger than or equal to every element of A. Right? Just use the inexhaustibility property and tack on equality, and then take the smallest one that satisfies that property. So there's always a least upper bound for any set of ordinals. This is denoted by sup A for supremum. And there is a smallest ordinal larger than all the finite numbers. So if we take the set of all finite ordinals, so that's a set, therefore we can take the smallest thing that's bigger than or equal to everything in the set, and that we will denote by omega, the lowercase Greek letter. Ordinals may be divided into 3 types. There's 0. There's the successor ordinals, which are one bigger than some other ordinal. And then there are the limit ordinals, which is neither. So it's neither 0 nor successor. For example, omega is a limit ordinal. It's the first limit ordinal. So using this setup, I'm now going to fix the proof. So we're going to define the rank function again, but this time we're going to define it more carefully. We're going to say that the rank of X is the supremum of one more than the ranks of all of the prerequisites. Notice, by the way, that if X has no prerequisites, then you'll be taking a supremum of the empty set, which is just 0. So it makes sense even if the set there is empty. Now we're going to follow the same proof idea as before. Notice that if y is a prerequisite for x, then the rank of y, well, it's certainly going to be strictly less than the rank of y plus 1, which is going to be less than or equal to the supremum of all those. So therefore, the rank of a prerequisite is always smaller than the rank of the course that it's a prerequisite for. Or in other words, the rank of any course is higher than that of any of its prerequisites, strictly higher. Now, 2 problems remain. First of all, did we fix the flaw? That is, does every course now have a rank? And secondly, the set of all ranks is no longer going to be just n. It could be much larger. So can we still assign each rank an interval, T alpha start, T alpha n, while fitting all such intervals inside 4 years without overlap? Okay, let's prove the first point. So let's show that every course has a rank. Well, let A be the set of all courses with no rank. Suppose that A is non-empty. Well, since C is well-founded, that means that A must also be well-founded, right? So if there's no infinite descending chain in C, there's certainly no infinite descending chain in A. So therefore, we can use the alternative characterization of well-foundedness. Let's take X to be a course in A that has no prerequisites in A. That means that for every prerequisite Y of X, Y cannot be in A. So if Y is not in A, that means that it does have a well-defined rank. But now X has a well-defined rank as well, because the rank of X should just be given by the formula in the previous slide. Because rank Y is defined. This is a contradiction. Therefore, A has to be empty. So there are no courses with no well-defined rank. That means every course has a well-defined rank, no matter how complicated the curriculum. Okay, for the second point, I'm going to show the following lemma. So for every countable ordinal alpha, there is a transfinite sequence of real numbers, T beta, beta going all the way up to and including alpha, such that it starts no later than 0, ends before 4, and it's increasing, strictly increasing. The T betas here are going to represent the starting times in the plan. So assuming we have this lemma, we let alpha be the rank of the curriculum. Specifically, what that means is it's the supremum of the ranks of all the courses in the curriculum. And then we're going to assign rank beta courses to the interval T beta t beta plus 1. So as I said, t beta represents the start times. And we might as well end just when the next rank is starting, unless beta is the final rank, in which case we assign it to the interval t beta of 4. That's why we needed the final t beta to be strictly less than 4. Okay, so now we just have to prove this lemma. And the proof is by transfinite induction. So there's the usual induction, proof by induction, which they teach in high school. And transfinite induction is just an extension of the usual proof by induction, except instead of inducting over the natural numbers, you induct over the ordinals. The way this works is that first you show that the lemma is true at 0. And then you show that if the lemma is true at alpha, that implies it's true at alpha plus 1. So that's just the same as proof by induction, but then there's one more step, which is that if alpha is a limit and the lemma is true for all beta is less than alpha, then it must also be true at alpha. So we just have to show these 3 things. Okay. Well, if alpha is 0, we can just take t0 equal to 0. And in other words, we'll just give ourselves all 4 years to complete the rank 0. So that's easy. For the successor case, suppose the lemma is true for alpha. That means that we can choose the starting times to fit inside 0, 4. Now we'll just divide all the starting times by 2, and then that means that we'll cram all the starting times into the interval 0, 2, and then we'll just stick in one more, the t alpha plus 1, to start at time 2. So that's also pretty easy. Now for the hard case and the new case, the case where alpha is a limit. Okay, so suppose alpha is a limit ordinal. Now, since alpha is countable, that means that the set of its predecessors can be enumerated. In other words, there's some listing of all of the ordinals less than alpha in such a way that every ordinal less than alpha will appear at some finite position in the list. So let alpha n be this list. What I'm going to do is I'm going to extract a subsequence, so a sublist of this list with the same supremum. Limit just means supremum here. We're going to let alpha 0 prime be just alpha 0. So it's going to start the same. And then to get the next thing in the new list, we're just going to search the old list until we hit the first thing that's bigger than our current term. And then we're just going to add that to the new list. So this gives us an increasing subsequence, alpha n prime. And should be pretty clear that the supremum of the new list is the same as the supremum of the old list, right? Well, it's a subsequence, so there's less things in it. So therefore, the supremum can't be any bigger, but it can't be any smaller either, because anything in the old list is less than something in the new list. Okay. Now what we're going to do is apply the induction hypothesis to each alpha n prime. All right. So we're going to shift and scale so that we're going to fit everything up to alpha 0 into the interval 0, 1. Then we're going to fit everything up to alpha 1 into the interval 1 to 1.5. So half of that previous interval. Then we're going to fit everything less than or equal to alpha 2 into the interval of half of the previous one, and so on and so on. Now there is one thing, which is that we have to delete repetitions because, well, alpha 0 is contained in alpha 1, and alpha 1 is contained in alpha 2. Sorry, by the way, there should be primes in all these alphas in this line. That's a typo, sorry. Anyway, so there should be primes here, and you have to delete repetitions because, for instance, alpha 1, everything less than alpha 1 is included in everything less than alpha 2, so you're actually repeating stuff. So you delete the repetitions, but that's fine. That doesn't add any points. That only removes points. So when you do this for all the alpha n primes, then we'll have fit all the indices in 0 to alpha into 0 to 2. And then we can just set the very last index to 2. And that's how you prove the lemma. And therefore, the lemma is true, and therefore we can fit all the courses into 0, 4. And that's the proof of the main theorem. Now, in the original version of this talk, that was the end. But thanks to some suggestions, I added some more slides to show some links to computability theory, part of theoretical computer science. So I'm going to assume you have some basic knowledge of Turing machines. And later we're going to see what happens if we apply this idea to a computer, a Turing machine that has this kind of power. Okay. The Church-Turing thesis asserts that any effectively calculable function can be computed by a Turing machine. That was the original statement. The phrase effectively calculable is informal. There are several different interpretations. One of them is that any deterministic and discrete procedure on finite objects that could clearly be carried out in real life, given sufficient resources, is effectively calculable. The thesis was inspired by the discovery that multiple theoretical models of computation all led to the same class of computable functions as that of Turing machines. The Church-Turing thesis is applied in two ways. Forwards, any realistic, quotation marks, carefully defined computation can be done on a Turing machine. And backwards, any function which is not computable on a Turing machine is not computable realistically. So the Church-Turing thesis establishes some limits on it's possible to compute. So the classic example of a non-computable function is the halting function. So let's phi sub e be an effective enumeration of all Turing machines, or equivalently, an effective enumeration of all computer codes in any sufficiently powerful programming language. So think to yourself, how do you enumerate all possible computer codes? Well, first we can order computer codes according to their length. The shortest computer program, right, is just going to be the empty program. And then after that come all the programs of length 1, then all the programs of length 2, and then all the programs of length 3, and so on. Well, what's a computer program? Well, you can specify it, right, by a list of symbols that are allowed in your programming language. The list is finite, so we might as well choose some order. And then we can just use a lexicographic order to order all of the programs of a specific length. So if you want an enumeration, an effective enumeration of all Turing machines, you just write down all of the possible strings of symbols that you use in your programming language, use a lexicographic order. So you prioritize the symbols in order that they appear in your code. And then you prioritize in order that order that you chose for the language. And then you throw away all of the nonsense programs, okay? Because programming languages always have some rules of syntax. Okay, so suppose you do that, then you get an effective enumeration of all Turing machines. Now, there's a classic result in computability theory that if you take this function h, given by h of en equals 1, if the eth program halts on input n, and h of en is 0 otherwise. So what is a classic result that h is non-computable. So there's no computer program that decides whether any computer program will halt on any given input or not. By the Church-Turing thesis, since Turing machines have this limitation, any realistic model of computation, so certainly any real-world computer, will also have the same limitation. So no computer can solve the halting problem. So while realistic computations are bounded by the Church-Turing thesis and hence cannot compute functions such as the halting function, we can still propose computational models that go beyond these limits. It's just that they won't be quote unquote realistic. They'll all involve some kind of magic. Some examples of this. Well, first of all, there are oracle machines. First proposed by Turing himself, these machines have access to some magic operation called an oracle that can return outputs of an otherwise non-computable function. For instance, you can imagine a Turing machine that, in addition to its basic operations, it can, go to the temple and pray to the halting god to ask whether the halting function is 0 or 1 at this number. So that's an oracle machine. Another example is an infinite precision machine. So that would be a machine that's able to store and operate on real numbers. By a real number, I just mean an infinite sequence of integers, or if you wish, an infinite sequence of decimals. So an infinite precision machine has to be able to store numbers to infinite accuracy. Of course, a real machine won't be able to do that. And then there are the infinite time Turing machines. These are Turing machines that are allowed to run for infinitely many steps. More specifically, an ordinal number of steps. As it turns out, infinite time Turing machines will have all of the power of infinite precision machines, and they may also have the power of oracle machines, depending on which oracle you're talking about. We'll see soon. All right, let me say some more about infinite time Turing machines. So a usual Turing machine, remember, has an input tape. And on that input tape, you write some input. Now, the rule is that the input has to be finite. But in an infinite time Turing machine, we allow infinite strings as inputs. Because since we have infinite time, we certainly have enough time to read an infinite string. All right. Now, infinite time Turing machines work the same as Turing machines, except we must specify what to do at the start of a limit step. So at successor steps, an infinite time Turing machine will do the same thing as a Turing machine, right? It has this finite set of states. It has a read-write head that's going to be located at some position on the tape. And then it'll just do what it's supposed to do at a successor step. But at a limit step, things are different because there's no predecessor step. So we have to answer some questions. So what should be the state of the machine at a limit step? 2, what should be the position of the read-write head? And 3, what should be the symbol at each position on the working tape? Hamkins and Lewis, 2008. So there's the paper on arXiv. It's given as the reference for this talk. They use an ITTM, sorry, this should be ITTM, not TM, with a binary alphabet. And so what should be the state of the machine? Well, they just they just mark one state and call it the limit state. And so at any limit state, the machine will always, so at any limit step, the machine will always revert to the limit state. What should be the position of the write head? Let's just move it to the starting position, 0. And lastly, what should be the symbol at each position on the working tape? They take the lim sup. What that means is that if alpha is a limit step and the symbol is 0 at all steps beyond some beta less than alpha, then you should set the symbol to 0 at the limit step. If not, that means that the symbol is 1, arbitrarily far up to alpha. And in that case, we set the symbol to be 1 at step alpha. So the lim sup function has an inherent bias towards writing 1 instead of 0. There is something rather magical about this operation, which is that normally Turing machines cannot remember their history, right? So a Turing machine doesn't remember computations that it did before, the way it's usually formulated. And for that matter, infinite time Turing machines don't really fully remember what they did in the past either, but they do have to have a small amount of memory here, right? Because you have to keep track of the lim sup operation uses the status of the tape at earlier steps. So it's kind of magical, but that's unavoidable because that's all you have to go on at limit steps. Because there's no predecessor. So you have to use, unboundedly many steps before. Okay, in the paper from Hankins and Lewis, they established the following properties of ITTM. First of all, the classic halting problem is decidable. So you can solve the halting problem. How? Well, it's pretty simple, right? If you have infinite time and you want to decide whether the nth classical Turing machine, whether the eth classical Turing machine halts at n, just simulate the machine and run it for omega many steps. And if it halts, then you'll notice. If it doesn't halt, well, then you'll also notice by step omega. But that's just getting started. You can go much further. So they also show that every statement of first order number theory is decidable. So that means every statement about the natural numbers involving only the basic symbols, equals, plus, times, less than alpha, and less than for all and there exists, is decidable. That's immensely powerful because there are so many unsolved problems in number theory. For example, if you want to solve the twin primes conjecture, the question of whether there are infinitely many twin primes, well, just check them all. You have infinite time, right? So I should say, by the way, why this is true. So it's a basic fact from first order logic that any sentence can be written in the form of alternating quantifiers. So for all there exists, for all there exists, for all there exists, followed by some atomic formula. So that means some kind of equation or inequality involving only variables of natural numbers. So what you would do then is that you can verify each individual instance in finitely many steps. And then every time there's a quantifier, you have the number of steps you need multiplies by omega, right? Because you have to check infinitely many instances, potentially. So that means, so the reason this is true is because, yes, you can just follow that idea. More specifically, the number of steps you need to decide a first order statement of number theory is going to be at most omega to the k, where k is the number of alternating quantifiers. Okay, here's a somewhat surprising result. Every run of an ITTM either halts or is eventually periodic. Now, this is not true of a regular Turing machine, right? A regular Turing machine could run forever without ever repeating, right? For example, just add 1, and then add 1, and then add 1 indefinitely. That'll never repeat, right? Because the output tape, the working tape, sorry, will just keep incrementing forever. But an ITTM will never do that. An ITTM will either halt or loop forever. So I can be more specific than that. So either the computation halts at some countable step alpha, or there's a countable limit step and a countable limit period tau, such that for every beta less than tau and for every gamma, the status of the computation at step alpha plus tau times gamma plus beta is identical to the status at step alpha plus beta. Now, I didn't tell you exactly how to define addition and multiplication of ordinals. It's actually a bit subtle, and but the intuitive meaning here is that the computation that at step alpha, the computation will start to loop with period tau. Okay, now I did want to tie this into what I was talking about earlier. So let me introduce, this is my own definition. An ATM, accelerated Turing machine, is an ITTM with timings. Specifically, for every run of the machine, there is a schedule, i.e. a sequence of start times and end times, T alpha start to T alpha n, where alpha is less than or equal to delta. A delta is the final step, countable, such that, you always have, so the first step has to start, of course, no later than 0, and you have to finish a step before you can start the next one. And delta is the first and only index for which T delta start is greater than or equal to 1. If the ITTM halts before stage delta, the ATM halts with the same output, and we call the schedule successful. If not, we say the ATM times out and the schedule fails. So we can say that an ATM is just is like an ATM with some restriction that you have to finish. The schedule should hopefully be successful. We may assume, without loss of generality, by the way, that we start at 0, the first step at 0. As soon as we finish one step, the next one starts, and delta's limit. Now, if ITTM does not halt, then there is no successful schedule. On the other hand, if ITTM does halt, then there is a successful schedule, but it might not be clear how to find it, because it might not be clear how to get a countable upper bound on the ITTM. So, for example, there's this example in the paper. So there is an ITTM that can decide whether a given encoding of a binary relation is a well ordering or not. And it turns out that this ITTM is runtime unbounded. That means for every countable ordinal alpha, there is an input on which the algorithm requires more than alpha steps to finish. So that means, yeah, it could take arbitrarily long countable times to finish a computation, which means, can be difficult to come up with these timings. There's more details in the paper. And that's the last slide. I guess one last comment I should make is that just like Turing machines, infinite time Turing machines also have their limitations. In particular, infinite time Turing machines cannot solve their own halting problem. This is maybe a little bit surprising because of the theorem a little earlier that by some countable stage, an ITTM will always either halt or loop. The problem is that even though the ITTM will loop, ITTMs only have countable memory. And, well, technically, the history of an ITTM is also countable, but the problem is that it's unboundedly countable. Therefore, there isn't really an effective way to code the memory. So the reason that ITTMs cannot solve their halting problem is that even though they loop, yes, they cannot recognize that they're looping. And, oh, yeah. That's what this says. This is a slightly more formal way of saying that. If we enumerate all of the ITTMs, and then we formulate the halting problem for that, then we get a non-computable function. So non-computable even in the ITTM. And the reason is it can't remember its computation history. There's also a one-dimensional version of the halting problem, which asks for which machines does the machine halt on input 0. Turns out this is also non-computable. That's the same as the classical case. But here's one thing that's different with the classical case, which is that the two-dimensional halting set is non-computable, even if you use the one-dimensional halting set as an oracle. So that's different from the classical case. In the classical case, the one-dimensional and the two-dimensional halting sets are equivalent. But in the infinite time setting, the two-dimensional halting set is in fact much stronger. And that's the end. Thank you.
Okay. Okay, thanks, Jen, for